In Module 3, we're going to cover the MX6 operations. Let's start by taking a tour of the physical features of the MX6. At the top of the instrument, underneath those openings, is where your sensors are located. We have to ensure that we keep this area free and clear of obstructions. This is the only place that the instrument will see gas. Therefore, we have to keep these areas free of obstructions. If we allow any dirt or contaminants to get clogged in the inlet ports, then the sensors will not be able to see the gas. If the sensors cannot see the gas, then the instrument will not be able to detect the gas. The chassis of the instrument is a composite material with a rubber overmolding, which helps against shock or during drops. Down the corner of the instrument is where a wrist strap can be connected. At the bottom of the instrument is where your battery charging connections are located. This is for charging the optional lithium-ion battery pack. Right next to that is the IR communication port. This is for communication with the data link or when connected with the DS2 docking station. There's a 5-way navigational button that allows the user to navigate through the different operations of the MX6. At the center of the instrument is your LCD display. At the top of the instrument, underneath that opening, is where your visual indication of alarm condition. Whenever any one sensor goes in alarm, all 4 LEDs will start to flash. There's a 5-way navigational button that allows the user to move through the different operations of the MX6. There's an up arrow and a down arrow. There's a left arrow and a right arrow. And in the center is an on-off enter button. With any gas detection instrument, it is always recommended that before you use it, to take it through the 4 steps of operation. Industrial Scientific Corporation designs, manufactures, and sells instrumentation for the preservation of human life and property. Recognizing this fact, it is recommended that the user send the instrument through 4 basic steps of operation to ensure maximum operational readiness and capabilities before each day's use. The first step of operation is always to turn on the instrument and to check the battery status. With this, we're also going to ensure that the proper sensor configuration and the proper sensors are installed in the instrument for the job at hand. The second step of operation will be to zero the instrument. Whenever we zero, we're using the ambient atmosphere as the instrument's zero reference point. 2 processes are going to take place when the instrument zeroes. The first process will be that the toxics in your combustible sensors will be set to 0 to eliminate any type of negative or positive drift. The second process that the instrument will do during zeroing is it'll calibrate the oxygen sensor to the room air at 20.9%. We always want to ensure that whenever we zero the instrument, that we zero only in clean air. If there's any contaminants in the air, that'll become part of the instrument's zero reference point. For example, let's say we zeroed the instrument, but in the environment was 5 ppm of carbon dioxide. When I go outside to a true clean air environment, my CO sensor will now read a -5 because the 5 ppm I told it was 0 will have disappeared and the instrument will have no choice but to then go negative. So we always zero in clean air. The third thing we're going to do with the instrument before we use it is we're going to take it through a functional test, otherwise known as a bump test. What a bump test is designed to do is to verify sensor and alarm operation. By applying calibration gas or bump gas to the instrument's going to then be challenged by the gas to ensure functionality, ensuring that the sensors do see gas, and when they see the gas, that they go into alarm. This should be done before each day's use. The last step before we use the instrument is to clear our peak readings. What peak readings are is the instrument will store the highest toxic and combustible reading along with the lowest oxygen reading since last time the peaks were cleared. Now, peak readings are used that if I'm in a confined space and the instrument starts going to alarm, the user's not going to want to sit there and start looking at the readings. Rather, they're going to want to exit. Now, upon exiting, they can then check the peak readings to see what that concentration was that they were exposed to. Since the instrument will record only the highest toxic and combustible and the lowest oxygen readings since the last time the peaks were cleared, the user would have no idea if they're their peaks or somebody else's peak from another time. Turning off the instrument does not clear the peaks. In fact, removing a battery pack will not clear the peaks. Peaks are stored in something called non-volatile memory, written in the code on the EEPROM. And the only way to clear these peaks is to take it through the peak clear mode. Now, the reason why we write them in the code, and the reason why they do not clear if you turn off the instrument, is for accident investigation purposes. God forbid somebody goes down on a job site with one of our instruments on their side. It may be a couple days before they find the body. The battery pack will long since be dead, but the peak readings will still be there, acting kind of like a black box showing the highest concentration that person was exposed to. By clearing the peaks as our last step, we're ensuring that any peak we see is our peak and not somebody else's peak from another time. So let's look at step number 1 of turning on the instrument. To turn on the instrument, we're going to press and hold the on-off enter button until the instrument actually turns on. The screens we'll see appear on the instrument during startup. This first screen will be the MX6 hybrid, showing us also the version software that is currently installed in that instrument. The second screen the user may see will be a contact screen. The contact screen gives us the web address and also the phone number of Industrial Scientific. The third screen that will come up will show us the sensors installed. With that, it may also show us user name and company name if so programmed into the instrument. And then I'll take us then to our real-time operation screen. Our real-time operation screen shows us the sensors installed along with the actual gas readings, but there are optional screens that may appear. These optional screens will appear if the instrument has been configured to show such screens. The first screens that may appear might show you either days until or the days since last calibration. Another screen that may appear if programmed is it may ask the user to zero the instrument during startup. The next screen up may ask us to bump test the instrument prior to use. Or it may actually come up and let us know that a new sensor has been installed. That way, if someone has reconfigured this instrument since last time it's been used, the user will get notification that this instrument is not the same configuration that they may be used to. What you're looking at now is the real-time operation screen. This is our regular gas reading mode. This is where we're actually detecting the gas in the environment. What you'll see is on the real-time operating mode, it'll show you the sensors installed along with its gas readings. Lower left-hand corner is your battery runtime indicator. There's little segments inside the battery runtime indicator to give you an indication of battery runtime. If the battery runtime indicator is completely filled with its indicators, then you have the full complement of runtime. But those segments will disappear, showing battery runtime loss. You also have a data log configuration that also may appear on a display letting you know how your data logger is currently configured. A PID response factor may also appear on your display as well. This is showing you how your PID is correlating its reading, and as we see in this example, the PID reading is going to correlate its reading in accordance with isobutylene. A time indication may also appear on the instrument to let you know the current time. Any gas reading that appears on the instrument's display in red is going to be an indication that that particular sensor is in alarm. Not only will the gas reading be red, but it's also going to increase in font to give us a visual indication that that particular sensor is in alarm. Our second step of operation is going to be to zero the instrument. To zero the instrument, we're going to press the on-off enter button 2 times, bringing up 3 different drop-down options: view, sensor, and data. By pressing a right arrow, we'll be able to highlight sensor. Pressing the on-off button, and it will then bring up zero all. At this point, it's going to ask me if I truly want to zero all of my sensors. Clicking OK will start the zeroing process automatically. The first thing the instrument will do is take my toxics and combustibles and set them to 0, eliminating any type of negative drift. The next thing the instrument will do is calibrate the oxygen sensor to the room air. We want to ensure that whenever the instrument is zeroing, that we zero only in fresh air, because the O2 calibration is going to be based on purely the ambient atmospheric conditions. So if your oxygen concentration is anything other than 20.9, it may skew your oxygen calibration. Upon completing the zeroing, the instrument will show you the condition of your zeroing. The little green passes indicate that those particular sensors have passed their 0, where a failed indication would be my indication that particular sensor has failed its 0. So once again, to see the zeroing of the instrument, we're going to press the center button 2 times, brings up a drop down, right arrow once to bring up 0, on off again, and if we press it a 3rd time, it's then going to ask us if we want a 0. Press OK, and the zeroing of the instrument will start. It's going to take your toxics and your combustibles and set them to 0 automatically. Upon completing this, it'll then automatically start the calibration of the oxygen sensor. So at this point, the oxygen sensor is calibrating itself to the room air. As we said previously, we always want to ensure we do this only in fresh air, because the O2 full span and that O2 calibration is based on the oxygen concentration in the ambient atmosphere. Once again, if this oxygen concentration is any other number other than 20.9, it's then going to show a skewed calibration. But upon completing this, it'll show you that the zeroings have passed. Pressing on off again acknowledges. On off again takes you back to real time. Our third step of operation is going to be to bump test the instrument. Prior to each day's use, Industrial Scientific Corporation recommends that a functional bump test be performed on the MX6. A bump test is defined as a brief exposure of the monitor to a known concentration of gases for the purposes of verifying sensor and alarm operation. If an instrument fails to operate properly following any functional bump test, a full calibration should be performed prior to use. So let's look at that step number 3 of bump testing. How we bump test the instrument is, first off, we're going to press the on-off enter button 2 times, bringing up our 3 drop downs. Right arrow again over the sensor. Now we're going to press the down arrow to highlight bump test. By pressing the on-off enter button, we're going to acknowledge that we're going to bump test all the sensors. By clicking OK, it'll actually start the bump test procedure. The first slide will appear, will show me that it's going to bump test and apply the calibration gas. Once I have my calibration gas flowing, I'm going to press the start button to start that bump test. At this point, it's going to actually start to bump test the shown sensor. My only other option at this point is to click abort. Clicking abort will then end the bump test of that particular sensor. Upon completing the bump test of that sensor, it's going to give me an indication of a pass condition. Upon completing the bump test of all installed sensors, it's going to show me a pass, a fail, or skipped. Green pass means that those sensors have, of course, passed their bump test, where a red fail indication would be an indication that the sensor failed the bump test. Skipped would be if I intentionally skipped or aborted the bump test of that sensor. Clicking OK will then allow me to move on. But if a sensor did fail the bump test, what appears on the instrument's display is sensor failed bump test, and it'll then request that I calibrate that individual sensor. By clicking the OK button will then put me in the calibration mode to calibrate that sensor. But if I select cancel and press the on-off button, the next slide will appear. Back in the real-time operating mode, what's going to be shown for that sensor that failed the bump test is the word cal. That cal is my indication that that sensor is at this point not detecting gas because it did fail its bump test. And to ensure I'm not walking around with an unsafe instrument, that cal is going to appear on the display until that particular sensor receives a successful calibration. So let's go ahead and look at an actual video. Once again, by pressing our on-off enter buttons to bring up our drop downs, we can then scroll over to sensor, pressing the down arrow to take us to bump test. Once we select bump test, we're now in the bump test operating mode. Clicking the on-off button will start that bump test procedure. At this point, we're going to start the gas flow, and then by pressing the center button for start, we'll automatically start the bump test of that particular sensor. At this point, we're just a spectator. There's nothing we need to do, but we do hear the instrument going into alarm indication of pass, showing us that that sensor is passed. The next sensor comes up, pressing the on-off again, starts the actual bump test of that sensor, and allows us to continue on with each individual sensor. Once all the sensors have passed their bump test, it's going to appear on the display that the bump test has completed. So now that the instrument has finished its bump test, it's going to give us the pass indication that all sensors have passed, and clicking OK takes us back to the real-time operating mode. At this point, we turn off our gas, pull off the cowl cup, and we let it clear out automatically. This is what's known as a menu type bump test. But there is another type of bump test that we could look at doing that isn't the menu version. Rather, it's a manual bump test. The bump test that we're going to be doing now is a manual version type bump test. The manual version type bump test is with the instrument on in a real-time operating mode. We're going to apply the calibration adapter and to start our gas flow. At this point, the gas is flowing to the instrument to challenge the instrument to the gas to ensure that your sensors not only respond to the gas, but also that the instrument goes into alarm. Once all my indicators have turned red, that's my indication of a successful bump test. Whether I do the manual type bump test or the menu driven type bump test, both bump tests are suitable. If I'm using the MX6 with the optional sample draw pump, a constant flow regulator cannot be used. Rather, I have to use a regulator known as a demand flow regulator. The demand flow regulator allows gas to be delivered to the instrument at the same rate at which the pump pulls the gas. If I use a constant flow regulator, the constant flow regulator is going to be delivering gas at a rate other than what the pump is demanding. Therefore, demand flow regulator must be used. If I still choose to use the constant flow regulator, I may. But if I use the constant flow regulator, I have to use something known as a T-fitting. You'll notice in the red box at the top of the tubing is my T-fitting. What the T-fitting allows for is for the excess gas to be vented out so that the instrument will only receive the gas it needs to do the bump test. But in order for this T-fitting to be successful, I have to ensure that the regulator's flow rate is greater than 0.5 LPM. The sampling pump of the instrument is pulling at a 1/4 liter per minute. Therefore, I have to ensure that the gas I'm delivering is greater than a 1/4 liter per minute, preferably greater than 0.5 LPM, to ensure that only excess gas is being vented and that the sampling pump is not pulling outside air in through the T-fitting. Okay, let's look at our last step of operation, which is clearing our peak readings. To clear our peak readings, once again, we're going to press the on-off enter button twice to give us our 3 optional drop downs. Using the right arrow over the sensor will allow us then to drop down our sensor options. From there, we can use our down arrow until it brings up peaks. From there, we press the on-off enter button again. What it'll show on the instrument's display is our current peaks. Once again, what the peak readings will show is the highest concentration of combustible gas and toxics, along with our lowest oxygen reading since last time the peaks were cleared. Now, naturally, before I use the instrument, I want to clear these peaks to ensure any peak I see is my peak and not somebody else's. So at this point, we would just simply hit the clear button. By pressing the clear button, it'll then ask us once again, do we truly want to clear our peak readings? By pressing OK, we'll clear out our peak readings and will then automatically be at the real-time operation screen. But let's look at some alarm conditions. We're going to look at a low alarm first. Now, in a low alarm, you're going to hear a single beep with the flashing LEDs, and a vibrating alarm will also be activated in the instrument. But in a high alarm, it's going to be slightly different. We'll still get the vibrating alarm indication and the visual indication, but when the instrument goes into a high alarm, the audible tone will be different. Rather than being a single beep, you'll hear a dual tone. The dual tone is our indication, our audible indication of a high alarm condition. Should a sensor exceed the gas concentration higher than the measuring range of that particular sensor, what will be displayed on the instrument is OR. OR stands for overrange. In other words, a gas has come in contact with a gas concentration higher than it's capable of displaying, and therefore OR will appear on the display. Now that OR will clear automatically for your toxic and your oxygen sensor once those gas concentrations drops down within the instrument's measuring range. But your combustible sensor is a little bit different. If the LEL sensor comes in contact with a gas concentration in excess of 100% LEL, it too will show OR. But not only will it show OR, but it'll lock that OR on a display, and at the same time your combustible sensor will power down. Your combustible sensor will turn itself off. The reason we want the combustible sensor to turn itself off in the presence of 100% LEL is purely to protect the combustible sensor from burning out. The combustible sensor detects combustible gas by burning the combustible gas, and the greater the concentration of combustible gas, the greater the burn. The greater the burn, the greater the heat, and that greater heat can actually cause stress to that catalytic bead and actually cause that bead to fracture. Older generation instruments that didn't have this feature built in would detect on a display 100, 150, 200% LEL until that little bead was cooking, until the bead would finally actually fracture. But what we've incorporated in the MX6 is something called LEL overrange protection, which means once I come in contact with 100% LEL, OR appears on the display, and the only way to clear that OR condition is to simply turn off the instrument and turn it back on again. If the MX6 is going to be used for confined space entry, it is always recommended, of course, that the sampling pump be in place over the instrument. The sampling pump allows me to draw a sample up to 100 feet, and the instrument should not be used for confined space evaluation unless this sampling pump is in place. Now before we use this instrument with the sampling pump, we always want to check the functionality of the pump by blocking the inlet port. By blocking the inlet port, we want to make sure we do get a pump fault indication on display of the instrument. This checks two things. One, it verifies that there is blockage in the tubing. I will be notified on the instrument display. And two, it also checks to ensure there's no splits or holes in the tubing, ensuring that the gas is only being drawn from one place, and that is at the end of the tubing. But there are certain sampling criteria that we ask the user to follow to ensure that a proper gas test of the confined space is being obtained. This is what we call the when, where, why of atmospheric testing. When we're going to sample from a confined space will always be prior to entry. We always want to sample prior to entry to see what we're getting ourselves into. But if I get out for a small smoke break or for lunch, I'm also going to want to sample prior to re-entry. Even though I've been out for a short period of time, I always want to sample prior to re-entry in case conditions in that confined space has changed from the short time I've been out. But not only do I want to sample prior to re-entry, but if I'm going into that confined space continuously, I'm also going to sample. Even though it was safe prior to entry, even though my readings were safe, I still want to continuously monitor while I'm in that confined space because I want to ensure that if the conditions inside the confined space change, that my instrument will then provide me notification of that change, because the work being provided in that confined space may be turning what we believe to be a safe atmosphere into a very dangerous one. Okay, but also where? Where are we going to sample from within the confined space? We always want to sample at the top of the confined space, the middle of the confined space, and at the bottom of the confined space. So we're going to sample the top, middle, and bottom. In the US, OSHA recommendation recommends that you do this in 4-foot increments. So you go top, 4 feet down, 4 feet down, 4 feet down till you get to the bottom of the confined space. And why? Why do we want to sample top, middle, and bottom not to exceed 4 feet? Because of stratification of gases. Some gases are heavier than air, some gases are lighter than air. Some gases may settle at the top of the confined space while others may actually drift or sink to the bottom of the confined space. Look at a gas like methane, for example, which is a lighter than air gas. It may actually stratify at the top of my confined space. Carbon monoxide, which is slightly lighter than air, will mix pretty well throughout the confined space but may stratify somewhere in the center. Whereas hydrogen sulfide, which is a heavier than air gas, may actually sink to the bottom. Now these gases may find their area of stratification if the gas concentrations are high enough. If the confined space has been buttoned up for a long enough period of time, these gases may actually start to find their areas of stratification. Now does that mean I can only find hydrogen sulfide at the bottom of the confined space? No. Get a little bit of ventilation in there, these gases can be found just about anywhere within the confined space. But by sampling at the top, middle, and bottom, I'm ensuring that if these gases have stratified, I will find their area of concentration. The last thing we want to keep in mind when drawing our sample from within the confined space is what? What are we going to sample for within that confined space? Well, according to 29 CFR 1910.146 subsection B, before an employee enters the space, the internal atmosphere shall be tested for the following conditions in the order given. And it's important that we do this in this order. We want to ensure that our oxygen content is between 19.5 and 23.5, and that our combustible gases are less than 10% LEL, and that our toxic gases are beneath the permissible exposure limit. Once again, though, you want to ensure that you are following company policies or local regulations when looking at these actual concentrations. The reason we want to always take note of our oxygen reading before we take note of any other readings is because oxygen is our #1 killer. More people die from an oxygen deficient environment than any other hazard in a confined space. But most importantly, it's going to also reflect directly on how our combustible gas readings will read. I need at least 10% oxygen for the combustible sensor to work properly. If I don't have at least 10% oxygen, my combustible gas readings will be erroneously low. Therefore, when I'm drawing a sample from within a confined space, if the O2 levels in that confined space are less than 10%, don't even look at the combustible gas readings because they'll be reading erroneously low. Provided I have at least 10% oxygen, I can look at my combustible gas readings with good faith knowing that the concentrations they'll be reading should be accurate. One aspect you always need to keep in mind when drawing a sample from the confined space is ensuring enough time for the sample to get up through the tubing and delivered to the sampling pump. This is something we call the 2 and 2 sampling rule. What the 2 and 2 sampling rules shows is that you want to allocate 2 seconds per foot of tubing, and then you want to add 2 minutes of sample time on top of that. The 2 seconds per foot is just to purge out whatever's in the tubing. The 2 minutes on top of that is to obtain the most accurate reading that you possibly can. So in an example of 20 feet of tubing, sample draw time would be 2 minutes and 40 seconds. 40 seconds will just purge out the 20 feet of tubing. The 2 minutes would then be used to obtain the most accurate reading that I possibly can. Let's look at some of the other display options available on your MX6. If you click the on-off enter button twice, it then will bring you up your 3 drop-downs. By clicking the on-off again on view, it's going to highlight automatically the word display. By clicking the on-off again, we'll bring up your numeric readings. By having numeric selected, it's going to allow your instrument readings in the real-time operating mode to show the gas concentration in the environment with the sensors that are installed. But if I choose text, my display will change. What will be shown on my instrument display now is I'll still have my sensors that are installed, but my gas readings will disappear, and in its place, little indications of OK, showing me that the gas readings for those sensors are OK. Should a sensor go into alarm, though, a low alarm will show the word low in red, or a high alarm will show the word high in red, giving me an indication that particular sensor is in alarm. Graphical is my last option. If I have graphical selected, now it's going to show me all my readings on a display graphically. But if I choose rotate for any one of my display options, it's going to actually rotate my display 180 degrees. This is so if I'm hanging the instrument up in a confined space, or depending on how I wear it on my person, I'll be able to then view the readings as if they're right side up for me. Also, another option we can look at under View and underneath Display by pressing the down arrow is Battery. By pressing my On/Off Enter button, my battery option will appear. My battery option will show me how much runtime is left in my battery in percentage. Underneath that is Profiles. By selecting Profiles, I can actually have a pre-programmed profile programmed into the instrument with a particular username or site location attached, so I can configure the instrument for different operations depending on the skill level or the needs of that particular individual. By programming up these individual profiles, one instrument can be used to satisfy many different needs. Underneath Profiles, by pressing my down arrow, will bring up my Help feature. Under Help, I have two different options that are currently available on the MX6. One of them would be Contact ISC. This is our contact screen showing you our web address and our phone number. I could also bring up About. About simply shows me which instrument I have in my hand and the revision micro that the instrument is programmed with. When we're looking at the battery available for the MX6, it is available with a variety of different battery sources. We have a rechargeable lithium-ion battery pack. Will give you about 24 hours of typical runtime. The other battery pack is an extended range lithium-ion battery pack. This will extend the runtime up to 36 hours. And the last battery pack that you may find available for your MX6 is a replaceable AA alkaline battery pack, giving you about approximately 10.5 hours of runtime. The battery runtime indicator located in the lower left-hand corner of your display will indicate approximately how much battery capacity is left. If you see all the indications filled in the battery, then we know that we have a 100% fully charged battery pack. But if one of the indications is missing, then we're down to about less than 75% of the battery capacity. Only two little hashes remaining within the battery indicates about a half-charged battery pack. If I have one little indication in there, well, I know I'm down to my last quarter worth of runtime. A yellow battery, though, would be my indication that my battery pack is down to less than 5% capacity and will soon show a low battery indication. So if I have less than 10 minutes of runtime remaining, the instrument will alert the user of the impending shutdown by displaying low battery. At this point, the instrument should no longer be used and placed back on the charger, or another battery pack should be put in its place.